Bismillahirrahmanirrahim. Welcome to the channel. My name is Asim Amjad, and in this video lecture we still discussing the lecture number 10, that is elastic beam bending. In this video lecture we actually look the properties of sections. So we will learn how to find area moment of inertia, that is I. As I said before, the area moment of inertia in our previous video lectures was the integral over the A of R squared times dA, and it was a cross section's resistance to the bending about a certain axis. We can find the area of moment of inertia by integrating directly, but many textbooks have the standard tables for different shapes of cross section that we will work with. So we can take those standard shapes and we can combine them in a composite shape by using a parallel axis theorem for moment of inertia, which is shown here. Parallel axis theorem actually it gives the relationship between the moment of inertia with respect to a centroidal axis and the moment of inertia with respect to any parallel axis. The general definition of parallel axis theorem for moment of inertia is the moment of inertia of an area with respect to any axis in its plane is equal to the moment of inertia with respect to a parallel centroidal axis plus the product of the area and the square of the distance between the two axes. Here you can see the moment of inertia about its neutral axis is equal to the moment of inertia of standard shape's neutral axis plus area times d square. So let's go ahead and do an example. Let's look at a standard shape which is a rectangle, and if you look that up in a reference you will find that the moment of inertia about the x-axis is going to be 1 by 12 times base times height cube. So now let's use that standard shape for an example of the cross section. So first of all I'm going to divide this shape into three standard shape. I will have a rectangle at the top, a rectangle here in the middle, and rectangle at the bottom. And I want to find the I, that is moment of inertia, about the neutral axis for the composite cross section. And so we will take this first rectangle here, and that's going to be its I about its neutral axis is equal to 112 times the base, and the base is here A, times its height cube, that is B cube, plus the area of that standard shape, that is A times B, and the distance from the overall composite neutral axis to the neutral axis of the standard shape, which is D1, that is D1 square. And we will do the same thing for the next standard shape, which is this rectangle in the center. So that's going to be plus 1 by 12 base time height cube. In this case the base is D and the height is C cube, plus the area of this standard shape, that is C times D, and the distance from this standard shape neutral axis to the neutral axis of the overall shape, that is D2. And finally for the last shape, which is the rectangle at the bottom, so we have 1 over 12 time base, that is f, and the height is e, so f e cube plus area of this rectangle is e times f times the distance from this standard shape neutral axis to the overall standard shape neutral axis, that is d3 square. So that's the total moment of inertia for the composite shape. So as we go forward with actual examples, we will actually put the numbers in and calculate a value for a moment of inertia. Thank you.